So what are the largest glaciers in the world? That was the focus of my project. To recap the project goals, I plan to perform a global analysis of glaciers, beginning by exploring the 19 recognized glacier regions and then finding the largest glaciers for each region and then for the world. In addition, I plan to study global glacier melt to see which glaciers are disappearing the fastest and which have disappeared completely. This is highlighted in yellow here because I was not able to get to that part of the project during this class. I will continue that work later. Why is this project important? Well, glaciers are melting at an alarming rate due to climate change. This melting, also known as a glacier retreat, is contributing to sea level rise. Glaciers are also an important source of fresh water and hydroelectric power for many nations. As glaciers disappear, these nations will need to find alternate forms of water and energy. In addition, glaciers are places of beauty used for recreation. Studying glaciers helps to inform our knowledge of climate change and helps water and energy resource managers plan for the future. Researchers have performed many regional studies of glaciers. However, global studies are scarce. That is why I chose to perform a global analysis. My approach to this project was to analyze 2 global glacier datasets and start by finding the 10 largest glaciers for each of the 19 regions from both datasets and then compare the lists. I didn't choose to look for the top 10 right away, but decided to do this when I saw mismatches between the 2 datasets when looking at the top 3, and found that when I looked at 10, I would see, for example, that number 2 for GLIMS might be number 5 for RGI. This was informative, so I went with that approach. If the list didn't match, I investigated why and then pared down my lists to the 3 largest glaciers for the 19 regions. Finally, I found the largest 3 glaciers for the entire globe. This project, at first glance, appeared to be a rather straightforward task, but turned out to be quite challenging, as I will explain in coming slides. But first, let's explore the 19 glacier regions. Here you see a map with each of the regions drawn out. They're labeled on the world map. For example, Region 1 here is Alaska, Region 11 is Central Europe, and Region 19 is Antarctic and Subantarctic. These regions are defined by the Global Terrestrial Network for Glaciers. I used 2 datasets for this analysis. The first was the Global Land Ice Measurements from Space, or GLIMS. GLIMS is a project designed to monitor the world's glaciers, primarily using data from optical satellite instruments, and it provides the glacier outlines at multi-temporal resolutions for glaciers around the world as shapefiles. The second was the Randolph Glacier Inventory, or RGI. This dataset is a globally complete inventory of glacier outlines intended to be a snapshot of the world's glaciers as they were near the beginning of the 21st century. It provides measurements at only one point in time for each glacier as a shapefile. The GLIMS data is provided in one large shapefile containing 383,780 glacier outlines. To work with the GLIMS data, I first needed to split the GLIMS data into the 19 regions. I did this using GeoPandas and a shapefile of the 19 regions I obtained from the Global Terrestrial Network for Glaciers. Once I had split GLIMS into the regions, I then wanted to only use the most recent measurements, so I filtered by the latest date. This gave a total number of outlines over 19 shapefiles of approximately 300,000 glaciers. I then determined the area of each shapefile and selected the 10 largest for each region and saved this to a CSV file for later use when comparing to RGI. You can see my workflow diagram at the bottom of the screen. For the RGI data, much less processing was needed before using it because they came pre-packaged into the 19 regions, and since it only provides measurements for one date, I did not have to filter. The RGI dataset provided 216,502 glacier outlines. I then determined the area and created a corresponding CSV file of the list. You can see the workflow diagram for the RGI data at the bottom of this slide. Finally, I compared the list of the top 10 for each region from both datasets. If they didn't match, and they didn't match about 40% of the time, I investigated why by checking dates of measurements and always taking the most recent one. If the dates were similar, then I checked remote sensing data and published literature to learn more. As I mentioned earlier, there were quite a few more challenges with the comparison than it appeared at first glance. There was, of course, the mismatch of temporal coverages between GLIMS and RGI, which was easy enough to solve by choosing the most recent measurement. The other issue that had proven to be a bigger challenge is when the lists don't match well at all. When the lists matched well, as seen in Region 1 in Alaska in the table on the left, where only the bottom two highlighted in yellow were different, it was easy to choose the top three for the region. However, if you look at Region 6, Iceland, in the table on the right, you'll see that none of the top 10 glaciers matched. So why was this? The reason that Region 6 is so different is in the way that GLIMS and RGI define what a glacier is. This image of Vatnajökull Glacier in Iceland on the right shows that GLIMS defines the whole area as a glacier, as seen by the red outline here. However, RGI defines Vatnajökull as a glacier catchment with multiple glaciers inside of it, as seen by the green outlines, these here. So one of the challenges is to determine how to handle these cases. To complicate matters, RGI doesn't always break glacier catchments up into individual glaciers. This inconsistency means I have to manually inspect all glaciers. The picture on the right here is of Bahia del Diablo Glacier in Antarctica, which depicts the problem photographically. This glacier has 3 tongues, or sections, that come off of the main ice cap. This could be broken into 3 glaciers, or it could be represented as 1 depending on the definition of glacier. Also, RGI doesn't have the same number of glaciers as GLIMS does. GLIMS has 300,000 glaciers, a little over, where RGI has about 216,000. While I'm still working out the details of how to define a glacier and how to cull this out of the 2 datasets, I do have some preliminary results. I want to cover just one region of the 19 regions, as covering all of them would be tedious to listen to, and we don't have time for that. So here I show Region 1, Alaska. Since it is pretty familiar to most people in the audience, and there was a good agreement between both GLIMS and RGI. Here, you see an overview of the map of Alaska region with the largest 3 glaciers plotted on top of the base map. You see Bering Glacier in green on the left, Seward Glacier in orange in the middle, and Hubbard Glacier in red on the right. But let's take a close-up view of these. When we zoom in, we really see all the detail of each glacier. This image on the right shows the 3 glacier outlines superimposed over a Google Earth image. The largest of the 3 is Seward Glacier in the middle in orange with a size of 3,363 square kilometers, or approximately 1,300 square miles. That's slightly larger than the size of the state of Rhode Island, which is a fairly large glacier. The second largest is Bering Glacier in green with a size of 3,025 square kilometers, and the third largest is Hubbard Glacier on the right in red with a size of 2,835 square kilometers. The image at the bottom left here is an aerial photo of Bering Glacier. I provided here for context. You can see the long tongue of Bering Glacier in the aerial photograph matches the outline you see overlaid on the Google Earth image on the right. So let's move on to the largest glaciers for the whole world. Here we see the 3 largest glaciers in the world according to GLIMS. On the left, we see the largest glacier, which is Vatnajökull Glacier in Iceland with a size of 8,092 square kilometers, or approximately 3,100 square miles. This is about 2/3 the size of Connecticut. As I explained earlier, however, RGI does not define this whole region as a glacier the way GLIMS does, so giving this the title of largest glacier is still up for debate. The second largest glacier in the middle, shown in green, is the Flod Isblink ice cap in Greenland with a size of 7,538 square kilometers. And the third largest, shown in red on the right side, is Seller Glacier on the Antarctic Peninsula with a size of 7,018 square kilometers. So if we look at RGI, what does it say the 3 largest glaciers in the world are? Number 1 comes in as Flod Isblink ice cap in Greenland. Number 2 is Kearney ice cap in Antarctica. And number 3 is Seward Glacier in Alaska. As I mentioned earlier, RGI doesn't always break up ice caps into separate glaciers, so these top 2 are also up for debate. Also, as you can see, if you break up the ice caps, the largest glaciers tend to be closer to the size of Seward Glacier, shown here, the size of about 3,300 square kilometers. So you can really see the difference. This is 3,300 square kilometers for a glacier, but ice caps tend to be twice or more than twice that. So what does all of this mean? Well, it means I still have more work to do to determine what an appropriate definition of a glacier is and how to calculate the area of those if my definition doesn't match the ones that GLIMS and RGI use. I also still need to do more literature searches on these glaciers, create the webpage for the NSIDC website, and then explore Glacier Retreat. I'll be working on this for a while. Thank you for your time, and let me know if you have any questions.